And here's our next example. So we're given that the rate of growth of the population is proportional to the existing amount, and it is given by dy dt equals 0.05 times y. In addition, it's given that y of 0 equals 200. So initially, there were 200, whatever it may be, where there's bacteria growing, where there's a population growth, there were 200 objects present. Determine an equation that represents the function y of t, which is basically the population size at time t. Okay, so we're going to start from scratch, not assuming anything. And basically, we're going to follow the same steps from the previous video. So if dy dt equals 0.05 times y, and if we're trying to figure out what y of t is, basically, we need to solve for y in this equation. And what we learned in the previous segment was there's a technique called separation of variables. You put all the y's on the same side and all the t's on the other side. So we're going to begin with that. So let me multiply both sides by dt. So dy equals 0.05 times y times dt, and at the same time you can also divide both sides by y. That way all the y's are on the left now and the t's are on the right. And at this point we're going to integrate both sides to get rid of the derivatives and try to solve for y. So integral of 1 over y dy, we have learned that previously is ln of the absolute value of y. And because we're dealing with a positive quantity, like the size of a population, I'm not going to use the absolute value right now. I'm just going to say ln of y equals, and the integral of a constant times t, we have learned is that constant, in this case 0.05, multiplied by t plus c, to make it more general, because c could be any value. To get rid of ln and to solve for y, we're going to need to exponentiate both sides. So let's do that. So e to the ln, basically, you could write it that way. You could say e to the ln y, but they cancel each other, and you end up with y on this side. And on the right side, e to the entire right-hand side, 0.05 t plus c. Now that can be simplified a little bit and written as e to the 0.05 t times e to the c. And I went over this in the last segment, but just a quick refresher, if you're wondering how I can separate it like that, well, think about going backwards. If you're going to multiply these two quantities on the right side, since the bases are the same, you would be adding the exponents, right? So you can verify that if you multiply these, you're actually going to get e to the 0.05 t plus c. And so this is a pretty common technique to split the quantity. And the reason we do that is because then we're going to call e to the c yet another constant. Let's say constant c. You could call it a capital C. The first one could be lowercase, just another constant. So we can then rewrite our quantity as y equals a constant times e to the 0.05 t. And there's, normally we're done. We found a function, but it has a constant and unknown value. But this time they give us an extra information, sometimes known as an initial value condition. They said at time 0, the population size was 200. So let's use that information here to determine the value of c. Okay, so we're going to plug in, so go ahead and plug in a 0 for t. So c times e to the 0.05 times 0. So now e to the 0 is 1. And this whole thing should be equal to 200. That was given in the problem. So therefore, we automatically get from here that c is equal to 200, right? And now that you have determined what c is, you can go ahead and plug that into the equation. So take this equation and go ahead and plug in your c value. So y equals 200. Here, all of them are the same constant, but I'm using my fancy c here. Okay, so y equals 200 times e to the 0.05 t. So that is the function that represents the population size at any time t. So just to recap everything, we went with a simple assumption that the rate of growth of the population was proportional to the existing amount. In this case, they gave us the proportionality constant. It's growing at a rate of 5% of the existing amount, so 0.05 times y. And then they give us additional information that y of 0 equals 200. Just from that information, using those two together, we were able to find the actual function that represents the population size at any given time t.